Designing circuits. So our goal of this lab is to be able to find the resistivity and resistance of a homemade Plato resistor. The importance is that resistors and circuits have become very important to the world we live in because they allow things like houses, phones, and many other things we take for granted to work. The main question that we're doing for this lab is that we're wondering what's the resistance of the homemade Plato resistor within a parallel circuit that keeps one loop of an LED light working and another loop of a motor working with the Plato in the LED loop.
For this lab, the physics concepts that we used include Ohm's law, the resistivity formula, as well as Kirchhoff's first and second laws. We also used resistance in a parallel circuit equation, where 1 over resistance of all resistors in parallel equals the sum of all the resistors in the parallel circuit. For this experiment, Kirchhoff's laws helped us to understand how voltage and current in a circuit changes at each loop and element. We also need to find out the resistivity of the Plato resistor. Using Ohm's law and the resistivity formula, we can determine the value. Also, using these formulas, we can understand how altering our resistor impacts the overall resistance it has in the circuit.
As you can see in our circuit diagram, we have two parallel loops, and so the current coming out of the battery will be split between those two loops, but the voltage going across them will be equal to 3.9. Since each loop has a series of the resistor and the motor or LED, or the voltage between those two will be split between the resistance of each thing. So here's our Plato model, and knowing the resistivity formula, we know that resistance is dependent on length and area. So knowing that, we can alter the Plato in order to change its resistance. And so in that case, we took the measurements of the area and the length of the Plato.
For our experimental design, we created two parallel circuits, one loop containing the cylindrical Plato resistor as well as an LED light, and the other loop containing an ohmic resistor and the motor. Using a voltmeter and the ruler, we were able to measure the voltage and the current through our circuit and the dimensions of our Plato resistor. We originally experienced problems with the LED not lighting up, and we tried making the Plato resistor larger and smaller, but saw no noticeable result. In the end, we also added a resistor to the motor loop and saw illumination with the LED light. Some flaws and limitations of an experimental design include the Plato, which can't be kept consistent throughout the duration of the experiment and whose resistance would change with moisture, shape, and volume. The metal probes used for attaching to the Plato could also have oxidized, making current flow harder, altering our data. The metal probes can't be perfectly connected to the Plato, so the small distance that they're pushed into the Plato can alter how the resistance works.
Through our data collection, we found the following values, shown on the screen. I battery is the total current through the entire circuit. I1 is the current flow through the ohmic resistor to the motor, and I2 is the value of current found from the Plato to the LED. In order to find the total resistance, we used a number of equations. First, we took the total voltage of 3.9 and divided it by the total current and got 3.7. We then used that 3.7 to plug it into the 1 over R parallel equals all the other resistors in the circuit. Doing this, we got that the Plato resistance would be around 3.7 ohms, which is the same as what was going on through the entire circuit. Now, this obviously doesn't make sense and has caused a great deal of uncertainty with our calculation. Additionally, we took the voltage drop across the Plato and divided it by the current that was flowing through the Plato and got 19,125, which seems a little too large for our Plato resistor. So another way we tried to find the resistance of our Plato was we took the resistivity average from our pre-lab and we plugged into the resistance formula and got a resistance of 43.45 ohms. We believe this resistance value to be the most accurate as it is low in magnitude and consistent with other groups. So some of our reasonings that may have caused this uncertainty with our data was mainly due to time constraints, as we were unable to determine the resistivity of the motor and light bulb. This would have helped us to try and obtain a more accurate measurement for the resistance of the Plato. Additionally, we believe that the current reading across the Plato was performed incorrectly. If this current reading was wrong, the potential correct current through the Plato should be around 18.3 amps instead of microamps. This would give us a resistance of a few magnitudes smaller of around 0.019. For talking with Group A, we determined the resistance should be around 10 to 30 ohms. This therefore leads us to believe that the data collection was performed incorrectly. Another source of error may have been due to improper measurements of the Plato shape.
In conclusion, we were able to determine the effect of adding resistors to parallel circuits and the effect that it would have on the total circuit. We were able to take voltage and current readings from various points on the circuit and use both Ohm's law and the resistivity formula to calculate the resistance of our Plato resistor. Using the resistivity formula, we could see the effect that changes in area and length of our resistor had on the overall resistivity of the resistor. Through this lab, we also found that across loops in a parallel circuit, voltage will be the same, but the current will want to divide, flow being proportional to the loop with the least resistance.